deep in the Atacama Desert, where the air holds almost no moisture and the nights stretch clear and cold above the world's highest plateau, radio dishes turn their faces towards space with the patience of ancient monuments. The Atacama Large Millimeter Array spreads across this desolate landscape like a field of metallic flowers, each dish precisely calibrated to catch the faintest electromagnetic whispers from the cosmos. Here, at an altitude where oxygen grows thin and the atmosphere barely filters the universe's constant chatter, 66 antennas work in perfect synchronization, creating a synthetic eye larger than any single telescope could achieve. The desert itself seems designed for this purpose. Rainfall measures less than 15 millimeters per year, creating conditions so dry that mummified grass from the last ice age still lies preserved on the plateau's surface. Water vapor, the enemy of radio astronomy, exists here in concentrations so low that the atmosphere becomes nearly transparent to the electromagnetic spectrum. Indigenous peoples once called this place the Puna de Atacama, the high grassland of silence, never knowing how perfectly their name would suit humanity's quest to listen to the universe's deepest secrets. Tonight, as every night for years, computers process terabytes of data streaming down from the receivers, searching for patterns that don't belong to the familiar symphony of cosmic background radiation. The Milky Way's own emissions create a constant hum, punctuated by the sharp crackle of lightning on Jupiter and the gentle sighs of hydrogen clouds condensing in distant stellar nurseries. Radio astronomers know this soundscape by heart, can distinguish between the electromagnetic signatures of quasar jets and the death throes of colliding neutron stars as easily as a musician identifies instruments in an orchestra. The signal appears first as a gentle anomaly in the data stream, a repeating burst that pulses every 1635 days with mechanical precision that seems almost deliberate, unlike the chaotic flares of distant quasars or the lighthouse sweeps of pulsars. This pattern carries something different, something that makes the night shift astronomers lean closer to their monitors and double-check their calibrations with the methodical care of people who know that the universe delights in surprising those who think they understand its rules. Each burst lasts exactly 2.347 seconds. No more, no less, with a consistency that makes atomic clocks seem imprecise by comparison. The signal strength varies slightly, sometimes strong enough to trigger automatic alerts that wake astronomers in laboratories across 3 continents, sometimes barely distinguishable from background noise, but the timing never wavers by more than a few microseconds. Whatever generates these emissions maintains its rhythm across millions of years of travel through intergalactic space, where temperature hovers 2.7 degrees above absolute zero, and matter exists in densities so low that a single hydrogen atom might drift for millennia without encountering another particle. The frequency itself tells a story. At 142 GHz, the signal occurs precisely at the hydrogen line, the natural emission frequency of the universe's most abundant element. This cannot be coincidence. Hydrogen atoms throughout the cosmos emit radiation at this exact frequency when their electrons flip spin states, creating a background hum that radio telescopes detect from every direction in space. For an artificial signal to broadcast at this frequency suggests either remarkable coincidence or deliberate choice, as if the source intentionally selected the one frequency that would be universally recognized by any civilization capable of radio astronomy. Astronomers call these mysteries fast radio bursts when they flash once and disappear forever into cosmic silence. But this signal returns again and again, patient as geological time and twice as mysterious. Most fast radio bursts originate from within our own galaxy or its nearest neighbours. Brief flickers of energy from magnetar starquakes or neutron star collisions. But this repeating pattern comes from much farther away beyond the local group of galaxies, beyond the Virgo supercluster, from regions of space so remote that light from the cosmic microwave background has barely had time to cool since the universe's birth. The origin lies somewhere in what astronomers politely call the cosmic web's filamentary structure, the vast scaffolding of dark matter that connects galaxy clusters across billions of light years. Here, in the spaces between the spaces, where galaxies become isolated islands separated by voids larger than human imagination can comfortably grasp. Something maintains a radio beacon with persistence that defies explanation. Only the most sensitive instruments can detect it, filtering the signal from the constant background hiss of the universe, cooling since its birth 14 billion years ago. The mathematics alone suggests something extraordinary beyond conventional astrophysics. Radio waves at this frequency and intensity require energies equivalent to converting several Earth masses directly into electromagnetic radiation, more power than our Sun produces in an entire year, released in precise bursts across a transmission that spans longer than multicellular life has existed on Earth. Yet the pattern shows no signs of decay or deterioration, no indication that its source grows weaker with age or distance. Whatever mechanism creates these emissions operates with efficiency that borders on the thermodynamically impossible, converting energy into radio waves with almost perfect consistency across cosmic time. In the control room, where coffee grows cold in forgotten cups, and astronomers speak in whispers that won't disturb the delicate instruments. Monitors display cascading waterfalls of data. Each pixel represents a fraction of electromagnetic spectrum captured across millions of light-years of space, transformed into colours and patterns that reveal the universe's hidden architecture. The repeating burst appears as a vertical line, straight and consistent, defying easy explanation among the chaotic swirls and spirals that characterize most cosmic phenomena. Solar flares create more violent patterns, spreading across multiple frequencies in unpredictable bursts that follow the 11-year cycle of magnetic pole reversals. Stellar explosions bloom once and fade, leaving only expanding shells of cooling gas that will glow faintly for thousands of years before dissolving into the interstellar medium. Even the most exotic neutron stars wobble slightly in their rotation, creating subtle variations in their emissions that astronomers use to map their magnetic fields and measure their distances through parallax observations. But this signal maintains its rhythm with clockwork regularity that would impress the makers of the most precise chronometers. The source appears too massive and stable to be any known type of star, too organized and persistent to be natural in any sense that current physics can explain, yet too distant and powerful to be artificial in any way humans understand technology. The pattern resembles nothing in the catalogues of known cosmic phenomena, yet it carries the unmistakable signature of reality, too complex to be instrument error, too persistent to be coincidence, too distant to be terrestrial interference, too regular to be random chance. Something out there in the darkness between galaxies keeps perfect time across eons, broadcasting into the void with inexplicable determination. Each pulse carries information encoded in its precise timing, its frequency stability, its polarization patterns that rotate through space in ways that suggest the signal passes through magnetic fields of unimaginable strength and complexity. The signal travels at light speed, of course, meaning the bursts detected tonight began their journey when the Milky Way occupied a slightly different position in its rotation around the local galactic cluster. Stellar motions have carried our solar system thousands of kilometers from where it was when these particular radio waves began their journey across the cosmic dark. The mathematics of this wandering fascinate astronomers who spend their careers calculating trajectories through space and time objects that follow no predictable elliptical paths, no comfortable orbits around gravitational anchors, but instead drift through the galaxy like leaves on an invisible wind. Orbital mechanics, that most precise of sciences, breaks down when applied to objects unbound by gravity's gentle chains. Every first-year astronomy student learns Kepler's laws, the elegant equations that describe how planets sweep equal areas in equal times around their parent stars, how orbital periods relate to distance in perfect mathematical harmony. But these laws assume gravitational binding, the persistent tug of a massive body that keeps smaller objects dancing in predictable patterns around a common center. Rogue objects, planets ejected from their birth systems, asteroids flung into interstellar space by close encounters with gas giants, comets perturbed from stable orbits by passing stars follow hyperbolic trajectories that lead nowhere and everywhere simultaneously. Their paths through space describe mathematical curves that approach straight lines as they escape the gravitational influence of any star, achieving what physicists call escape velocity, with margins so large that no force in the galaxy can recapture them. Computer simulations model these wandering paths with Monte Carlo techniques, running millions of possible trajectories to map the probability clouds where such objects might travel. The calculations reveal how chaotic three-body interactions can transform circular orbits into parabolic escapes within a few thousand years. A planet orbiting peacefully around a binary star system for millions of years can find itself suddenly accelerated beyond recovery when a third star passes too close, its gravitational field creating resonances that amplify small perturbations into catastrophic instabilities. The nearest known rogue planet, designated WISE 0855 or 7114, drifts through space just 7.3 light-years from Earth, close enough that its faint infrared signature appears in sensitive surveys that map the sky for brown dwarf stars and planetary mass objects. This world, roughly 5 times the mass of Jupiter, maintains a surface temperature of negative 48 degrees Celsius, far too cold for liquid water, yet warm enough to suggest an atmosphere still thick with methane clouds and water vapor from its formation billions of years ago. Astronomers estimate that such objects outnumber stars in our galaxy by ratios that strain comprehension. For every sun visible in Earth's night sky, perhaps 10,000 invisible worlds drift through the spaces between stellar systems, carrying no light of their own, detectable only through their gravitational influence on background stars or the faint heat they radiate into space from radioactive decay in their cores. The Milky Way contains perhaps 400 billion stars, suggesting trillions of rogue planets wander through territories so vast that most will never approach another star closely enough to feel its warmth. These calculations assume random ejection velocities and directions. But what if some rogue worlds follow more organized patterns? Galactic rotation creates streams and currents in the distribution of stellar motion, invisible highways that channel objects along preferred trajectories through space. The galactic tide, subtle gravitational effects from the Milky Way's spiral arms and central black hole might influence how rogue planets move through interstellar space, creating coherent flows that persist for millions of years. Recent observations from the Gaia spacecraft, which measures stellar positions with unprecedented precision, reveal that stars don't move randomly through the galaxy, but follow complex streams and associations that trace their common origins in ancient star-forming regions. If stars move in organized patterns, perhaps the planets they occasionally eject do likewise, creating invisible currents of rogue worlds that flow along galactic rotation curves or spiral density waves. The repeating radio signal's source location aligns suspiciously well with one such predicted streamer river of ejected objects that models suggest should flow through the galactic halo at distances where individual stars become impossible to detect. Could the signal originate from a rogue planet following this invisible current? The timing of the bursts, their consistent frequency, their apparent motion through space all hint at something massive enough to maintain complex electromagnetic activity even in the absence of stellar heating. But conventional physics struggles to explain how an isolated planet could generate radio emissions powerful enough to detect across intergalactic distances. Planetary magnetic fields, even the strongest ones found in our solar system, lack the energy to broadcast at such intensities. The most magnetic planet known, the ice giant Uranus, generates radio waves barely detectable beyond the orbit of its outermost moon. Jupiter's emissions reach Earth only because of the intimate dance between its magnetic field and the volcanic activity of its moon, Io, creating electrical currents that accelerate charged particles to relativistic speeds. What mechanism could provide similar energy to a world drifting alone through interstellar space? Perhaps capture of a highly magnetic moon, torn from another star system during the gravitational chaos that ejected both objects into the cosmic void. Such a binary system-rogue planet and captured satellite might maintain tidal interactions powerful enough to drive electromagnetic phenomena across cosmic timescales. The 16.35-day period matches no known planetary rotation, but it falls within the range of orbital periods for large moons around gas giant planets. Or perhaps the signal indicates something even more exotic: technological emissions from a civilization that survived planetary ejection, maintaining artificial energy sources and communication systems during their world's journey through the galaxy. The precision of the timing, the choice of transmission frequency, the persistence across millions of years all suggest purpose rather than natural process. Yet the vast energies involved challenge any reasonable assessment of technological capability, requiring power generation on scales that dwarf anything in human experience. The mathematics grow more complex with each observation, requiring new categories of celestial mechanics to describe objects that wander through space, unbound by any star's influence, following trajectories determined by galactic rotation, dark matter distribution, and gravitational interactions with massive structures that remain largely invisible and poorly understood. Each possibility leads to calculations that push the boundaries of current knowledge, revealing how little astronomers truly understand about the universe's most remote and isolated objects. Only continued observation will reveal whether this mathematical mystery represents natural phenomenon or something unprecedented in the catalogue of cosmic radio sources. Meanwhile, the signal maintains its patient rhythm, broadcasting across the void with mechanical precision that suggests either exotic physics or exotic purpose, neither of which fits comfortably into current theoretical frameworks for how rogue worlds should behave during their eternal journey between the stars. The first interstellar visitor announced itself with the gravity of mathematics rather than the drama of discovery. On October 19, 2017, astronomers at the Haleakala Observatory in Hawaii noticed an object moving through the solar system with a trajectory that belonged to no known category of celestial mechanics. The object, initially designated A2017U1 and later renamed Oumuamua, a Hawaiian word meaning messenger from afar arriving first, followed a hyperbolic path that indicated origins beyond the gravitational influence of our Sun. Oumuamua measured roughly 400 meters in length and perhaps 40 meters in width, tumbling end over end through space in a rotation that suggested violent history. Its surface reflected sunlight with the dark efficiency of charcoal, indicating composition unlike any asteroid or comet previously observed in our solar system. Most remarkably, the object showed no signs of outgassing as it approached the Sun, no tail of sublimating ice, no coma of vaporized material, no brightening that would indicate volatile compounds responding to solar heating. Spectroscopic analysis revealed absorption lines consistent with organic compounds, complex carbon-based molecules that form in the cold depths of interstellar space, where ultraviolet radiation from distant stars slowly converts simple hydrocarbons into more elaborate chemical structures. These molecules, called tholins by planetary scientists, create the reddish coloration seen on the surfaces of distant Kuiper Belt objects and the organic haze in Titan's atmosphere. Oumuamua's surface bore the chemical fingerprints of millions of years in interstellar space, bombarded by cosmic rays and bathed in the diffuse radiation field that fills the void between stars. But Oumuamua carried more than just organic chemistry. Detailed observations revealed trace amounts of metallic elements iron, nickel, and heavier elements that require stellar nucleosynthesis to create. These signatures told a story of formation around a star very different from our Sun. Perhaps a more massive star that burned through its nuclear fuel quickly and died in a supernova explosion, scattering heavy elements into space where they eventually condensed into planetesimals and minor planets in a stellar system now long destroyed. The object's trajectory suggested an origin in the direction of the constellation Lyra, possibly from the vicinity of the bright star Vega. But Vega lies 25 light-years away, meaning Oumuamua would have required 300,000 years to travel from that stellar neighborhood to our solar system, assuming it maintained constant velocity through interstellar space. During such a journey, the object would have been exposed to temperatures barely above absolute zero, cosmic ray bombardment, and the gradual erosion of interstellar dust impacts that sandblast surfaces at velocities measured in tens of kilometers per second. The chemistry preserved in Oumuamua's surface provided a snapshot of conditions in interstellar space during the late Pleistocene epoch on Earth, when ice sheets covered much of North America and modern humans were beginning to migrate out of Africa. The organic compounds detected by Earth-based telescopes formed through processes that operate over millions of years, requiring patience that transforms simple molecules into complex structures through reactions that proceed one photon at a time in the near absolute zero of interstellar space. As Oumuamua approached its closest point to the Sun, instruments detected unexpected acceleration in its trajectory, a slight but measurable change in velocity that could not be explained by gravitational effects alone. This non-gravitational acceleration resembled the rocket effect seen in comets when sublimating ice creates jets that push against the object's motion. But Oumuamua showed no signs of outgassing or tail formation. The acceleration suggested either internal heating from radioactive decay or some exotic mechanism that conventional physics struggled to explain. The visitor's tumbling rotation period of 7.3 hours indicated either collision damage or tidal disruption during its journey through space. Objects formed in isolation typically develop stable rotation states through gravitational interactions with nearby material. But Oumuamua's chaotic tumbling suggested violent history, perhaps ejection from its parent system through close encounter with a gas giant planet, or fragmentation during passage through another star's Oort cloud, or collision with debris during its long journey through the galaxy. most mysteriously. Oumuamua's chemical composition suggested formation temperatures and pressures inconsistent with any location in our solar system. The object appeared to contain water ice and carbon monoxide in ratios that require formation in regions where stellar radiation levels and dust densities differ significantly from those found in our local stellar neighborhood. These chemical signatures provided clues about stellar formation processes in other parts of the galaxy, regions where heavier elements exist in different proportions than the cosmic mix that gave birth to our Sun and planets. Each spectrum obtained during Oumuamua's brief passage through the inner solar system revealed new puzzles about interstellar chemistry and planetary formation processes. The object carried information encoded in its mineral structure about stellar nucleosynthesis, supernova explosions, and planetary system formation that occurred billions of years ago in star-forming regions now dispersed across hundreds of light years. Reading this chemical record required techniques borrowed from meteoritics, geology, and atmospheric chemistry, disciplines that suddenly found themselves essential for understanding visitors from other star systems. The discovery of Oumuamua confirmed theoretical predictions that interstellar objects should regularly transit our solar system, carrying samples of material from distant stellar formation regions. Computer models suggest that such visitors arrive roughly once per year, but most pass undetected because they approach from directions where surveys don't routinely search, or because they lack sufficient size and reflectivity to appear in current sky patrol programs. Follow-up observations tracked Oumuamua until it faded beyond the sensitivity limits of even the largest telescopes, but not before determining its ultimate trajectory. The object will leave our solar system on a path that carries it toward the constellation Pegasus, where it will continue its journey through interstellar space for perhaps millions more years before encountering another star system. Its brief passage through our neighborhood provided humanity's first direct sample of interstellar material, a messenger carrying chemical information about stellar and planetary formation processes from regions of the galaxy that remain otherwise inaccessible to direct observation. The success of detecting Oumuamua encouraged astronomers to design more sensitive surveys capable of finding similar objects during their approach rather than after they begin departing. Such early detection would allow detailed study with spacecraft missions, possibly intercepting interstellar visitors while they remain within range of current propulsion technology. Each such object carries unique information about its stellar system of origin, providing samples of planetary formation processes that operated under different chemical and physical conditions than those that shaped our own cosmic neighborhood. Meanwhile, Oumuamua continues its solitary journey through space, tumbling slowly as it carries its cargo of organic molecules and heavy elements toward another chance encounter with gravity, perhaps billions of years in the future when the galaxy's rotation brings it near another star system, where curious astronomers might detect its passage and wonder about its origins in the cosmic deep. The ejection begins not with violence but with mathematics, a slow accumulation of gravitational perturbations that amplify over millions of orbital periods until chaos overwhelms stability. In a young star system where three gas giants dance in complex resonance around their parent star, planetary orbits gradually shift through gravitational interactions that follow no simple pattern. The innermost giant pulls the middle planet slightly inward during each conjunction, while the outermost world tugs it toward the system's edge, creating oscillations that grow imperceptibly larger with each passing millennium. For 30 million years, this delicate gravitational ballet maintains approximate stability despite the slowly building chaos. The middle planet, a world roughly twice the mass of Jupiter, with a thick atmosphere of hydrogen and helium wrapped around a core of rock and ice, follows an elliptical orbit, that carries it between the inner system's asteroid belts and the outer region's comet clouds. Its 4 large moons sweep through complex orbital resonances, their gravitational interactions creating tidal heating that keeps subsurface oceans liquid despite the system's distance from its red dwarf star. The resonance breakdown occurs during what astronomers call the late heavy bombardment phase of stellar system evolution, when remaining planetesimals and debris from planetary formation create a cosmic shooting gallery of gravitational perturbations. A massive comet, perhaps 50 kilometers in diameter, approaches the 3-planet system on a trajectory that passes close enough to the middle world to alter its orbital velocity by less than 1 meter per second, a change so small that it would be undetectable to observers, yet sufficient to push the planet's motion across a critical threshold where stability transforms into runaway instability. The cascade unfolds over just 10,000 years, barely an instant in cosmic terms. Each subsequent orbit carries the planet farther from its stable path, creating stronger gravitational interactions with its siblings that accelerate the instability. The outermost planet, following the widest orbit, serves as a gravitational slingshot that adds energy to the middle world's motion during each encounter, while the inner planet's proximity creates resonance effects that pump the wayward world's orbital eccentricity to catastrophic levels. During the final phase of ejection, the planet's orbit becomes so elongated that it approaches within astronomical units of its star during periastron passage, then swings out beyond the orbit of the system's outermost world during a pastron. The gravitational stress tears apart the delicate orbital architecture that once held the system in stable configuration. 2 of the planet's 4 moons spiral inward until tidal forces fragment them into ring systems, while the other 2 escape into independent orbits around the star, becoming minor planets in their own right. The ultimate ejection occurs during a close encounter with the inner gas giant that accelerates the rogue world beyond the system's escape velocity. In a single orbital passage lasting just a few months, gravitational forces add enough kinetic energy to the planet's motion to overcome the star's gravitational binding permanently. The world that once maintained stable orbits for millions of years suddenly finds itself on a hyperbolic trajectory, leading away from its birth star with velocity sufficient to escape not just the stellar system, but eventually the gravitational influence of the entire stellar cluster. As the ejected planet recedes from its former home, surface temperatures begin their inexorable decline toward the background temperature of interstellar space. This star that once provided warmth dwindles to a point of light indistinguishable from other distant suns, while the planet's thick atmosphere starts its long transition from a dynamic weather system to a gradually freezing shell of increasingly inert gases. Atmospheric circulation patterns that once drove storms larger than Earth slow and simplify as temperature gradients flatten and convection currents weaken. The planet carries with it a cargo of ice and rock in its remaining moons, now bound in orbits that will persist for billions of years even in the absence of stellar heating. These natural satellites provide the only significant gravitational interactions the rogue world will experience during its journey through interstellar space, their mutual orbital dynamics creating tidal effects that continue to generate internal heat long after the parent star's warmth becomes just a memory preserved in slowly cooling atmospheric layers. Magnetic field strength initially remains robust as the planet's metallic core continues generating electrical currents through convection and rotation, but the field gradually weakens as core temperatures drop and convection patterns slow. The magnetosphere that once protected the planet from stellar wind and cosmic radiation contracts closer to the surface, eventually providing only minimal shielding against the interstellar medium's charged particles and high-energy photons. During the first million years of exile, the planet's escape trajectory carries it through the outer regions of its birth stellar system, where gravitational interactions with distant Kuiper Belt objects and Oort cloud comets provide final opportunities for capturing additional material. Some asteroids and comets find themselves gravitationally bound to the rogue world, becoming satellites in highly elliptical orbits that will accompany the planet on its journey through the galaxy. The ejection velocity, approximately 47 kilometers per second relative to the system's center of mass, determines the planet's future trajectory through galactic space. This speed exceeds the local stellar group's escape velocity, meaning the rogue world will eventually leave its birth cluster entirely and join the population of objects that wander freely through the galaxy's spiral arms. Computer simulations suggest the planet will require approximately 2 million years to clear the gravitational influence of nearby stars and begin truly independent motion through interstellar space. As the last gravitational ties to its origin system finally break, the planet becomes a citizen of the galaxy rather than any particular stellar system. Its trajectory through space will be influenced by the Milky Way's rotation, the gravitational effects of spiral density waves, and occasional distant encounters with other star systems, but never again will it experience the stable orbital dance that characterized its first 30 million years of existence. The violence of ejection leaves no lasting scars on the planet's surface. The gravitational forces involved operate too slowly to create seismic disruption or atmospheric loss. Instead, the world begins its interstellar journey essentially intact, carrying its atmosphere, magnetic field, and remaining moons into the cosmic deep, where it will spend the next several billion years slowly cooling while traveling distances that dwarf the size of stellar systems. Only the changing sky provides evidence of the catastrophic orbital transformation. Constellations that remained fixed for millions of years begin their slow drift across the celestial sphere as the planet's motion carries it away from familiar stellar neighborhoods toward regions of the galaxy where different stars dominate the night sky, and unknown cosmic phenomena await discovery in the spaces between solar systems. The ejected world joins countless similar refugees from gravitational chaos, adding to the invisible population of rogue planets that astronomers estimate may outnumber stars throughout the galaxy. Each such world carries its own story of orbital instability and gravitational exile, creating a vast diaspora of homeless planets wandering through the cosmic dark with only the faint heat of radioactive decay and tidal interactions to sustain whatever processes continue operating in the absence of stellar energy. In the profound silence that follows ejection, temperature becomes the planet's most fundamental constraint and its most persistent enemy. The world that once basked in stellar radiation, sufficient to maintain atmospheric dynamics and weather patterns, now faces the inexorable thermodynamic reality of interstellar space, where the cosmic microwave background provides the only external energy source, a feeble 2.7 Kelvin that barely distinguishes empty space from absolute zero. Surface temperatures plummet with mathematical precision that follows the Stefan-Boltzmann law, radiating the planet's stored thermal energy into the void at rates determined by surface area and emissivity. Within the first 1,000 years of exile, atmospheric temperatures at the cloud tops drop below the freezing point of carbon dioxide, creating vast sheets of dry ice that begin accumulating in the planet's polar regions and high-altitude atmospheric layers. The once dynamic weather systems that drove circulation patterns across hemispheres slow to nearly imperceptible flows as temperature gradients flatten and convection currents lose their driving force. But beneath the surface, a different thermal story unfolds with the patience of geological time. The planet's core, formed through the gravitational collapse of iron and nickel during its birth in the stellar nebula 4 billion years ago, maintains temperatures approaching 6,000 Kelvin through the slow decay of radioactive isotopes embedded in its metallic structure. Uranium-238, with its half-life of 4.5 billion years, provides a steady flux of alpha particles that heat the surrounding material through electromagnetic interactions. Thorium-230 contributes additional thermal energy with an even longer half-life of 14 billion years, ensuring that internal heating will persist long after the universe itself grows cold and dark. This radioactive furnace operates with the reliability of atomic physics, immune to the external conditions that govern surface temperatures. Each uranium nucleus that undergoes spontaneous fission releases approximately 200 million electron volts of energy, a minuscule amount on human scales, but enormous when multiplied by the countless trillions of radioactive atoms distributed throughout the planet's interior. The cumulative effect maintains core temperatures sufficient to drive convection in the metallic core and lower mantle, preserving magnetic field generation and geological activity even in the absence of tidal heating from a nearby star. The temperature gradient between the blazing core and the frozen surface creates a stable regime of internal heat transport that operates through conduction and convection in the rocky mantle. Thermal energy flows outward from the radioactive core through crystalline rock structures at rates measured in millimeters per year, eventually reaching the surface where it radiates into space as infrared radiation, invisible to optical telescopes but detectable by sensitive thermal imaging systems. This geothermal flux amounts to perhaps 0.1 watts per square meter, 10,000 times weaker than solar heating on Earth, yet sufficient to maintain subsurface temperatures above freezing in regions where liquid water can persist. The planet's thick atmosphere, inherited from its formation in the outer regions of its birth star system, provides crucial insulation that traps geothermal energy near the surface, hydrogen and helium. The primary atmospheric constituents possess low thermal conductivity that creates an insulating blanket effect. As surface temperatures drop below the condensation points of heavier atmospheric components, methane and ammonia begin forming clouds and precipitation that further complicate the thermal structure of the lower atmosphere. Beneath ice caps that grow thicker with each passing millennium, pockets of liquid water persist wherever geothermal heating creates locally elevated temperatures. These subsurface oceans, similar to those detected beneath the ice shells of Jupiter's moon Europa and Saturn's moon Enceladus, maintain thermal equilibria that balance heat input from radioactive decay against heat loss through conduction to the frozen surface layers. The physics of these hidden seas operates independently of external stellar heating, creating isolated ecosystems that could theoretically support chemical processes and even biological activity throughout the planet's journey through interstellar space. Tidal heating from the planet's remaining moons provides additional thermal energy that supplements radioactive decay in driving internal geological processes. The orbital resonances between satellites create periodic gravitational stress that flexes the planet's interior, converting orbital mechanical energy into heat through friction and elastic deformation. This mechanism operates with particular efficiency during close approaches to other massive objects, rare encounters with rogue asteroids or distant passes near other star systems that temporarily perturb the moon's orbits and enhance tidal effects. the planet's magnetic field, generated by convection in its liquid metallic core, persists at roughly half the strength it maintained during its stellar-bound existence. The reduced field intensity reflects slower convection rates in the cooling core, but remains sufficient to deflect most cosmic ray particles and solar wind from other stars encountered during the planet's galactic journey. This magnetic shielding protects any remaining atmosphere from gradual erosion by charged particle bombardment, preserving the insulating properties that help maintain subsurface temperatures. Computer models of planetary thermal evolution suggest that this rogue world will maintain subsurface liquid water for several billion years, possibly longer than the remaining main sequence lifetime of its birth star. The radioactive elements that fuel internal heating will continue their decay processes according to physical laws that operate independently of stellar proximity, environmental conditions, or galactic location. Even as the universe expands and cools, eventually reaching temperatures lower than the current cosmic microwave background, these internal heat sources will persist. The thermal isolation of interstellar space creates conditions where energy conservation becomes nearly perfect, unlike planets orbiting active stars, where complex radiative and convective heat transfer mechanisms create rapid temperature fluctuations. The rogue world exists in an environment where thermal changes occur over millions of years. This stability allows for the development of thermal equilibria that persist across cosmic timescales, creating consistent subsurface conditions that remain nearly constant for durations longer than the evolution of complex life on Earth. Surface ice layers function as both thermal insulation and geological records, preserving information about the planet's thermal history in crystalline structures that reflect temperature and pressure conditions during their formation. These ice sheets, potentially hundreds of meters thick in polar regions, create pressure-induced liquid layers at their bases where temperatures rise above the melting point despite surface conditions hundreds of degrees below freezing. The deep freeze transforms the planet's surface into a landscape unlike anything found in stellar systems. Atmospheric gases condense into solid deposits that accumulate in vast plains of crystalline nitrogen, methane, and carbon dioxide. These frozen seas create unique geological features, dunes of solid xenon, mountain ranges of crystallized argon, impact craters filled with frozen noble gases that preserve records of the planet's journey through different regions of interstellar space, where gas densities and chemical compositions vary with galactic location. Yet beneath this alien surface, the planet maintains an interior that resembles worlds still bound to stars. Radioactive decay ensures that core temperatures remain sufficient for geological processes, magnetic field generation, and the maintenance of subsurface oceans where complex chemistry continues operating according to the same physical laws that govern planetary interiors throughout the universe. The rogue world discovers that life requires energy, not necessarily starlight, and that thermal energy from atomic decay provides as reliable a foundation for planetary habitability as fusion reactions in distant stellar cores. The search for invisible wanderers requires techniques that push observational astronomy to its theoretical limits, relying on gravitational effects so subtle that their detection demands precision measurements across years of patient observation. Gravitational microlensing, the most sensitive method for finding dark objects drifting through space, exploits Einstein's prediction that massive bodies bend the fabric of space-time sufficiently to focus light from background sources like cosmic magnifying glasses.